let's see if we can wrap up this assignment for Chapter 8 with number 65. Now, in problem number 65, they give us the enthalpy of formation of these. Get a pen here. The enthalpy of formation of this compound and this element and this element. And some of you are saying, what? I thought the enthalpy of formation of pure element was 0. Well, it's the enthalpy of formation is 0 if it's the pure element in its standard state. But in the standard state, sulfur is a solid. That would have an enthalpy of formation of 0, and the enthalpy of formation for fluorine is F2 as a gas in its standard state. So these enthalpies are not 0, and they're given to you. And then you remember that you can find the change in enthalpy of a reaction by summing the enthalpies. Excuse me. The enthalpies of formation of the products, and then subtracting the enthalpies of formation of the reactants. And so here we see that we have added the enthalpy of formation that was given us for sulfur and 4 of the fluorines. And now we're going to subtract the enthalpy of formation of SF4. And so what that's going to do is give us the enthalpy of this reaction right here. And you'll notice it's a positive number, and we would expect that because we're breaking these bonds apart. We're breaking these bonds here. We're breaking them apart. And in fact, there are 4 of them that we are breaking, and so that enthalpy for this reaction is for breaking 4 bonds, and so we divide that by 4 and we get 342.5. That D, remember, is the dissociation energy, the energy to dissociate that sulfur fluorine bond. Now the only difference here for the second part is we're looking at SF6. SF6. 6 fluorines out here like this, and so here we're going to be multiplying this by 6 fluorines, and so we'll get 1962 kilojoules. Divide that by 6 because we have 6 of the bonds, and so we get 327. Now it says the bond energy in the table is 327. So the value in the table must have been based on this calculation or this reaction. But remember, these bond energies required to break a bond are kind of an estimate because it does depend on the environment that this bond is found in. In this environment, there's going to be a little bit larger energy required to break the bond, and in this environment there's going to be a little less energy required to break the bond. And question C for number 65, why are the change in enthalpy values for sulfur and fluorine not equal to 0? Well, it's because they're not in the standard state. They're not in the standard state. They're not the most stable forms of the elements at 25 degrees Celsius. The most stable form are sulfur as a solid, and it's S8, and F2 as a gas. Now the change in enthalpy for these two things would be 0 for those species. And we have here a very similar kind of calculation to calculate the bond energy, the dissociation energy required to break this NH bond in NH3. And we see that this agrees pretty closely with, I think, with what's in a table. Let's look here and see, compare your value with that to table 8.4. And it's really close. So you calculated the bond energy to dissociate the DH or the NH bond, 389 kilojoules per mole.